Hello everybody, I hope you're doing well. This is a short video about sums, which is the very first section in the notes and exercises. More precisely, this is a video about summation notation, but we'll get to that distinction in a moment. For one thing, you all know how to add, so I don't really need to tell you about how to compute a sum or what a sum is, but our objective here is to talk about long sums, that is, sums that have lots of terms. So not things like 3 plus 5, but sums that might be adding up 50 numbers or 100 numbers or 1,000 numbers or even an undetermined number of numbers. So here's a small example of such a sum, right? So here's the sum on the left. And there's no mystery to what's going on there. You could figure out what that is equal to. Just take out your calculator or pencil and paper and add up 1 plus 4 plus 9, etc., up to 256. But what sort of characterizes the sum for our purposes here is that there are a lot of terms, and the terms have a pattern to them, right? The pattern here is that each term is the square of its order in the sum, right? So 4 is 2 squared, and 9 is 3 squared, and 16 is 4 squared, and so forth. And so what we're introducing here is really just an abbreviation. Instead of having to write out this big long sum, and this can get even more cumbersome as the sums get more complicated, we'll use summation notation, and this thing on the right hand side that is in blue now is an example of summation notation. So the pieces of this are, first, that symbol, that's the Greek letter sigma, so that's a capital S for sum, and that just indicates to us that this is a sum that we're talking about. And then what we'll do is we'll use a counter to keep track of the terms. Now there are 16 terms here. We start with 1 squared and we finish with 16 squared. So our counter will start with value 1, and that thing at the bottom of the sigma, that's the initial value of the counter, and it will count up to the number 16. So the number at the top is the final value of the counter. Our counters will always increment by 1. So if you're a student of computer science, you may be familiar with counters that have other kinds of increments, but our counters always start at whatever the bottom value is, so in this case 1, and if they start at 1, then the next counter value is 2, and then 3, and then 4, and then so forth, until you get to the top number, which of course is 16 here. And then next to the summation symbol, we'll put a formula that allows us to compute the term from the counter. And here the formula is just k squared, right? I just take the term number and square it, and that gives me the term. And you can see that this thing on the right-hand side is a much more compact way to express the sum. And it doesn't get any less compact whether there are 16 terms or 1600 terms. So that's a nice feature of the notation. All right, so let's flesh this out a little bit. Here's another example. Again, you can see I'm adding up kind of a lot of terms, but the terms have a pattern, right? They're all even numbers, 2 plus 4 plus 6 plus so forth. So the way I get from the term number to the term, and when I say the term number, this is the first term, this is the second term, the third term, and so forth. The way I get the term itself is I multiply the term number by 2, right? So the third term is 3 times 2, which is 6. The fourth term is 4 times 2, which is 8. The fifth term is 5 times 2, which is 10, and so forth. So I'll start my counter at 1. The term function will be 2k, because to get from the term number to the term, I multiply by 2, and I need to go up to k equals 100. So our first goal here is to be able to go back and forth between sums written out the long way, like that's highlighted in blue, and sums written out using summation notation. And we do want to be able to go in both directions, to take a sum written out the long way and compact it, and also to take a compact sum like this and expand it. Those will both be useful things for us to be able to do. So here's another example, right? So now I start on the right-hand side, this time on the left-hand side rather, pardon me. I'm starting with the summation notation, right? And so again, the sigma cues me that it's a sum. My counter now starts at 2. The counter could start really at any number, and it goes up to 200. So how do I unpack this sum? I start with the first counter value, k equals 2, and I plug it into whatever the formula is. In this case, I just take the counter and add 2. Well, 2 plus 2 is 4, so that's my first term. Then I increment the counter by 1. So the counter started at 2. So when I increment it, it goes to 3. And again, I plug into my formula. 3 plus 2 is 5. So the next term is 5. Then the counter goes to 4. 4 plus 2 is 6. There's the next term, and so on. And I keep going until the counter hits the top value, which is 200. And 200 plus 2 is 202, and that's where the final term in the sum comes from. So for long sums like this, we typically need an ellipsis, right? So that dot, dot, dot is called an ellipsis because there's so many terms, we don't want to have to write out all of them. All right, a couple more examples and eventually some properties of these things. So another example, here's my summation on the left-hand side. This time the counter starts at 5, it goes up to 100, and the formula is 3 times the counter plus 1. All right, so first counter value is 5. I plug into the formula, 3 times 5 plus 1 is 16, so that's the first term in the sum. I increment the counter by 1, so it goes to 6. 3 times 6 plus 1 is 19. That's the second term. Increment the counter to 7. 3 times 7 plus 1 is 22. Yep, there we are. There's the third term, and so forth. And I stop when the counter reaches the top value of 100. 3 times 100 plus 1 is 301, the final number in the sum. And again, we use an ellipsis, so we don't have to write down every single term in the sum. A couple more, although probably this is getting pretty clear already. So one point to be made by this example is what letter we use for the counter doesn't really matter. We typically will use letters like K, I, J, N, like lowercase letters from the middle of the alphabet tend to be the sort of preference, but it doesn't make any difference. Any letter will do as a counter, right? So here, my counter is, I'm using the letter N for the counter. 2 is the initial value. It goes up to 100. And the formula is I take the reciprocal of the counter, right? So I start with the first value, 2. 1 over 2 is 1/2. So that's the first term. Increment the counter to 3. Plug into the formula. 1 over 3 is the second term. Increment, plug in. 1 over 4 is the third term. Stop when you get to counter value 100. And 1 over 100 then will be the final term in the sum. Again, we have an ellipsis. Whether you write the ellipsis sort of down bottom or in the middle doesn't really matter as long as it goes between the plus signs. Okay. I will note that as we start to encounter more complicated sums in the coming sections, sometimes our sums will include a variable besides the counter. So you can see in the formula here, there are actually 2 variables. Note, of course, pi is not a variable, it's a number, it just has a symbol attached to it. K is, of course, the counter. I can tell that because of what's highlighted in blue there. But N is just some other unknown. I unpack and repack this sum in exactly the same way. The counter starts at 1, so when I plug in K equals 1, I get 1 times N pi over 3, or just N pi over 3. Then I increment the counter to 2 and plug in K equals 2. That gives me 2N pi over 3. Increment the counter to 3, I get 3N pi over 3. And notice that if this K is a 3, it's going to cancel with the 3 in the denominator, giving me just N times pi. And then I keep on going, and 47 is the last counter value. Again, the point of this example is to distinguish between the counter K and other variables that might be in the sum. In this case, N, which is kind of just along for the ride. So when I plug in the K equals 47, I get 47 N pi over 3, which is the final term in the summation. Alrighty. One sort of footnote here, this is not super important, but something to be aware of, is that summation notation is not unique. That is, a sum like this, I can express using summation notation in lots of different ways. Here's an example. And I'm going to take exactly that sum from up above, right? So I just kind of copied it down. And I want to note, I claim that this is actually exactly the same sum as that thing highlighted in blue, even though they look different, right? The counters have different start values, and there's a different formula. But when I unpack the sum, right, I start from the low counter value of 4. And when I plug in K equals 4, I get 4 minus 3 squared, which is 1. And then I increment the counter to 5, and I plug in, I get 5 minus 3 squared, which is 2 squared, or 4. And then the counter goes to 6. 6 minus 3 squared is 3 squared, or 9, and so forth. And you can see that I'm unpacking exactly the same sum that I was before. So if it were a problem, let's say, to take this sum, whoops, let me try that again here on the right, and write it in summation notation, these are both correct. They're both correct answers. I think we have a preference for this one because it's simpler, and simpler's always better if you can get away with it. So again, not something to worry about a lot here, but something to be aware of, that there's more than one way to put something into summation notation. And sometimes summations that look different are actually the same sum. Not always, but sometimes. Okay, so a few special sums and ways of manipulating sums. First, a sum with constant terms. So here, hopefully, is an example of that, indeed, right? So this means I have a summation, and the term formula is just a constant. That is, the counter doesn't show up in the term function. So my sum here has a counter of k that goes from 1 to 50, but the formula is just the constant 6. Well, if I unpack this using our rule for summation notation, I take the counter value 1, that's where I start. I plug into the term function, but I just get 6 when I do that, so there's the first term. Then I increment the counter to 2, plug into the term function, but again, every time I plug into the term function, I just get 6 because it's a constant term function. So I still get a sum here. It's sort of an odd one, right? I just get 6 plus 6 plus 6 plus 6, and I get 50 copies of 6 because the counter went from 1 to 50, so there's 50 terms in the sum. Of course, this is just multiplication. If you add 6 to itself 50 times, that's 50 times 6, and I guess just for completeness here, we can note that that's equal to 300. In general, if we take a constant and we add it to itself n times, right? So this is the symbolism for that. If k starts at 1 and counts up to n, then I have n copies of the constant c, which is just equal to n times c. So this is sort of a useful thing to keep in mind. It comes up occasionally in dealing with summations. Another sum that we can analyze a little bit, and the analysis comes from this picture. So I have here an array of different colored dots, right? There are blue dots on the lower right and purple dots on the upper left. And the way to think about this is the number of blue dots is I have 1 blue dot here, and then 2 in the next row down, and then 3 in the next row down. And if we expand the picture a little bit, let's expand the picture a little bit. One more, right? So 1 blue dot, and then 2 blue dots, and then 3 blue dots, and then 4 blue dots. So the number of blue dots is 1 plus 2 plus 3 plus 4 plus 5 up to however big the picture is. The purple dots have exactly the same count because the sort of triangle of purple dots is the same as the blue triangle. It's just kind of upside down. So the total number of dots in the picture, because it's a grid, is the number of rows times the number of columns. In this case, there are 7 rows and 6 columns. You can go ahead and count them up. So I have 42 dots, 6 times 7. Half of them are blue and half of them are purple. And so this gives us a way of counting the blue and the purple dots. And the importance of this is I can use this to compute the sum 1 plus 2 plus 3 plus 4 plus 5 up to any number. Up here, we're talking about up to 6. But if we made this rectangle huge, the reasoning would still be the same, right? The total number of blue dots is 1/2 of the total number of dots in the picture, and the number of dots in the picture is rows times columns. Well, the number of columns is just whatever you're adding up to, in my case here, 89, and then the number of rows is 1 more than that. So that's where this formula, 89 times 90 over 2, comes from. In the picture that is on the screen now, what we are looking at, let's go ahead and add a little something here, is the sum up to 6, right? And we're saying that that's equal to 6 times 7 over 2, right? Which is just this formula right here, 1/2 times 6 times 7. And the point that I'm trying to make here is it doesn't matter how far this sum goes, the same reasoning works. It's always this number times it plus 1 divided by 2, and this gives us a nice formula for summing the first n integers, right? For doing this sum 1 plus 2 plus 3 plus 4 plus 5, and so forth. And here it is sort of in symbolic terms. If notice that the formula here depends entirely on where you stop the sum. I take that number times itself plus 1 divided by 2. So if the stop value is n, I take n, I multiply by n plus 1, behind my cursor, and I divide by 2. Okay, so this is useful. So there's some more examples to come later, but if this sum were, say, up to 1 million or something like this, this would be, you know, 1 million times 1,000,001 over 2, and that's not hard to do on a calculator. On the other hand, actually adding up the first million integers, even with a calculator, that's going to be a pain, right? It's a tedious calculation to do. So there is some advantage to this little formula. A couple of other similar formulas, and explaining these is beyond our scope, so we will just accept that they work. You can, in fact, come up with formulas for the sums of any powers of the first n integers, and here are the formulas for the first n squares and the first n cubes. Now, the good news is that this is a remote online class, so you don't need to memorize these formulas. You can always just look them up in these notes that will be posted on the Canvas page. But you should be aware that they're there, so that if you see an expression like this, you'll know, there's a formula for that. I just need to go get it so that I can use it to compute this sum. Okay, so here is an example. This is the sum from up above. It was one of the earlier examples, right? The sum of the first 16 squares. And we now can use this formula to evaluate that sum. Notice that n is the upper limit of summation. It's the stop value of the counter. So in our example, it's 16. And when I plug a 16 into this formula and plug that into my calculator, it comes out to be that. And in this case, you can pretty easily check that that's right. Just take and add up all these numbers on your calculator, and it should come out to 1,496. All right, a couple of other properties of sums, and some of these will sound familiar. You've all heard of the distributive property, and this is what the distributive property looks like in summation notation, right? If I have a sum like this, so notice here, counter is k, goes from 1 to n, and a sub k just represents some generic formula with a k in it. Could be anything, k squared, 1 over k, 3k minus 1, right? We've seen a few examples. C is a constant, just a number. You'll notice that there's no k anywhere in C. Well, if I expand this sum, here's the k equals 1 term, c times a sub 1. And here's the k equals 2 term, c times a sub 2, and so forth, right? I get this big sum if I unpack. And the distributive property says you can factor out the constant. You've done this plenty of times when doing algebra. And so if I factor out the constant, it looks like this. And then if I take this sum and repack it in summation notation, it looks like this. And if I go from far left to far right, a consequence of this is if I have a summation that has a constant multiple in it, I can pull that constant multiple outside the sum. Again, sometimes useful when we're working with summations. For example, if I take this sum, I can see that the 4 is a constant, right? It's a constant multiple of the k. K is not a constant, it's the counter. So I can factor 4 outside the sum, like that. And then this sum is just the sum of the first 23 integers, and we have a formula for that, right? That's the n times n plus 1 over 2 formula. And so I can replace that with the 23 times 24 over 2, and I get whatever this comes out to be. Can I do that quickly? No, I don't think I can. So let's have the computer do it for me. 4 times 23 times 24. This software that I'm using, by the way, is called Mathematica. You do not need Mathematica for this class. And anything I'm doing here, you could do on a calculator or on the web somewhere, right? So I'm just doing that out, and it comes out to 1104. There we go. Okay, and then we don't need that anymore. Another property of sums is that if I have a summation that contains a sum, right? So for example, something like this, where the term formula, which is this thing, contains a sum. It's a sum of two different formulas, a sub k plus b sub k. Then I can split the sum into two separate sums, the sum of a sub k plus the sum of b sub k. And that's true whether the plus sign there is a minus sign as well. So for example, and this sum, is this one we looked at up above, k plus 2? Sort of. We had a different upper limit, but we looked at a sum that was very similar to this one before. All right, at any rate, let's look at what we can do with our new rule here. I see that my term function, this thing, has a plus sign in it. It's the sum of two different term functions. And because of this property, this means I can split the sum into two pieces, right? The sum of the first term function, k, plus the sum of the second one, 2. And now I recognize that this first summation is the sum of the first 50 positive integers, and the second one is just the sum of a bunch of constants, and I know how to do both of those, right? For the first one, I use the n times n plus 1 over 2 formula. Here it is. And for the second one, if I add 2 to itself 50 times, I get 50 times 2. And so here I have something that I can easily do on a calculator. And the virtue of these rules and formulas is that even if this sum had 5,000 or 500,000 terms, this calculation wouldn't be that much more difficult. They'd just be bigger numbers on your calculator. All right, let me use my computer to see what that is. 50 times 51 divided by 2 plus 50 times 2 is 100. I can do that. 1375. All right, there we go. Let's get rid of that. Okay, a couple of examples, and that will be good for this short video. First, consider this sum, right? So this is a pretty substantial sum. Just looking at it, I can see I have 700 terms, right? The counter starts at 1, and it goes up to 700. I could start writing them out if I were so inclined, although I don't know that I gain a lot by doing that. If you plug in a k equals 1, let's see, 3 minus 2 is 1 plus 6 is 7. If I plug in a k equals 2, 3 times 4 is 12, 8, 14. Okay, I've had enough already, right? And that will go up to a final value when k is 700. So let me just kind of plunk that down here. We'll replace the k's by 700s. Whoops. There. Okay, but let's use what we know about sums to figure this out in a more sophisticated way. So the first thing I'm going to do is I'm going to split it up because my term function contains sums and differences, and I can split up sums and differences, which is what you see in the first line here, where I've split it into 3 separate sums. Notice that on each one, the counter range is the same, always 1 to 700. And I've got here my first term and my second term and the third term. And then in the next step, I'm going to look at these first 2 terms and realize that I have constant multiples, right? The 3 and the 2 are constant multiples. And I can factor those out because of another property of summations. So I can pull a 3 out of the first one, and I can pull a 2 out of the second one. And while I'm working on this here, I can see that this third sum is just the sum of a bunch of constants, right? It's 6 added to itself 700 times, and so that's going to be equal to 700 times 6. Okay, well, this formula is the sum of the first 700 squares. This is the sum of the first 700 integers. There are formulas for those. I can go look them up and plug the 700 in, and this is what happens if you do that, right? So I've just taken those formulas from up above. Here's one, right? This is the one for the squares. Here's the other one for the first 700 integers. Plug in 700, and I get something now that I can do on a calculator without too much trouble. And I come up with this, right? 343248850. Okay, one more example, and that'll be good. And this one actually looks even easier. I can see I have 43 terms, right? Counter starts at 1, goes to 43. My term function is 2k minus 1. The first thing I'm going to do is split this up because I can see my term function has a minus sign in it. Right? That is to say, it's the difference of 2 term functions. So this is what happens when I split this up into 2 sums, right? The counter range is the same. First term formula is 2k, second one is 1. I can factor out the constant 2 in the first one, right? So that looks like this. And here, I'm just adding the number 1 to itself 43 times, which is just 1 plus 1 plus 1 plus 1. That comes out to 43, or 43 times 1. And finally, this, of course, is the sum of the first 43 integers. We have a formula for that. So if you go grab the formula, it's the n times n plus 1 over 2, 1, plug in, and I get something. Notice that what we're able to do in these examples basically is compute a sum despite it having a lot of terms. And my calculator says that's equal to 1,849. And one final thing I want to make you aware of that I think you're probably already aware of, but just in case, there are lots of calculators and computing tools online for you to use. Of course, if you have a traditional handheld calculator, that's just fine. If not, or if you just don't want to go to the drawer to get it, Google Calculator is a pretty good one. If you just Google Calculator, this is the thing that will come up, and you can see that you can just sort of click the buttons and do calculations here, right? So what was this one we did? 2 times 43 times 44 over 2, 2 times 43. You can also type the numbers, times 44 divided by 2, and then what was the rest of it? Minus 43. Minus 43, and then equals 1849, and that's the same thing we got. Yes, indeed. So just making you aware of that thing that you're probably already aware of. Okay, so that's good for section 1.1 on sums. Take very good care of yourselves, folks.